Boa tarde, obrigado. Thank you for the invitation from the Portuguese Passivhaus Association and Homegrid, and congratulations for the organisation of the conference, and thank you all for being here. It's great to be in Portugal and share experiences about Passivhaus and low energy building, and it's really good to see. I am a Passivhaus consultant living and working in Barcelona. I set up an engineering company there 8 years ago, and people said to me, "You're crazy. You want to start working in the construction sector in the middle of a huge economic crisis in the worst sector of the economy possible, and you want to do Passivhaus?" People said, "You're crazy." But we kept working, and we've moved forwards, and I would say 85% of our work is related to Passivhaus or low energy buildings. So it can be done. It's like Germán said, there's no reason not to do this. It can be done, and it's economically viable, and it's technically viable. So I just wanted to present a small project that we were involved with as Passivhaus consultants, which was an EnerPHit retrofit project in Girona in Spain, in just north of Barcelona. So, yeah, a little bit along the lines of Germán's question. In Spain, why would you bother with Passivhaus? You know, it's all sunshine, it's basically quite warm, there's beaches. You could probably say the same about Portugal. You know, you've got a temperate maritime climate. Why bother with all of this, you know? Well, there's lots of reasons to bother with Passivhaus, but one of these is, in Spain, for example, since the economic crisis, average household income has decreased, and of course fuel expenditure has increased. So that's giving rise to a situation of fuel poverty, which is a feature in a lot of European countries. EnerPHit can help fill that gap, because obviously as people, if their net earnings decrease and their energy expenditure goes up, you know, savings have to be made, and EnerPHit can help with that. Ironically, in Spain as well, there's a situation where some of the highest levels of fuel poverty are in the hottest parts of the country. That's Andalusia. 15% of families can't keep the right temperature in their home. In Catalonia, where the project is, are at 9%. And then the Canary Islands, which is the happiest climate you could probably find, there's still 15% of families who can't keep their homes at the correct temperature. So this is one of the many reasons, I think, for doing a proper, deep energy retrofit of existing buildings with Passivhaus. So the project I'm going to present is not, it's not social housing at all. It's more high-end flats, but it's located in Girona, which is in the northeast of Spain, about 60 kilometers inland, and the project itself is located here in the city center of the old town. So just to run through the project, it was certified as Passivhaus EnerPHit with the demand method as a pilot project. The original building was built in 1978. It's about 1,000 square meters of gross floor area. The specific build cost of the whole job was around 1,100 euros per square meter, so not exactly cheap. The developer is a local developer who decided to opt for Passivhaus and took the step to do this project. That was a contractor, the architects based in Barcelona, service engineering of PGI Engineering. We were responsible for the PHPP Passivhaus design and building physics and the control system, and the certification was done by Energy House Arquitectos. So the build took a year, began in August 2016, and it was finished in 2017. So I'll just run through some of the details of the project. Before that, just briefly, EnerPHit, it offers us two different ways to get to certification. One is the energy demand method, and the other is the component method. I'm sure a lot of you already know this, but just to summarize, the energy demand method is very similar to Passivhaus Classic, so it's a performance-based certification where you have to meet the limiting space, heating and cooling demands. It's more demanding, and it's probably more advisable where you can use large amounts of insulation on an existing building without causing risk from moisture damage. If that's not possible, the component method is the alternative where you have to meet limiting U values. So it's less demanding, but it's also safer if you have to do an internal insulation system. And of course there's common requirements, which is the 1 air change per hour at 50 pascals, which needed to be met either way. So in this project we went via the energy demand method. These are the results of the PHPP. So for the Girona climate, we had a heating limiting demand of 20, cooling of 15, and the air tightness of 1. If we look at the local climate, these are the average monthly temperatures. So we've got about a 10-degree average temperature during the heating period and around 20 degrees in the summer. So at least on the average monthly data, it doesn't look too extreme. However, if we look at the local temperatures, for example, the absolute minimums and maximums, it does get quite cool, minus 8 in January 2017, and it got up to 36 degrees in July of last year. So it can get quite cool and it can get quite warm. So just some information of the existing building. This is the, in the image on the left, the main facade that's south-facing. So basically there's a load-bearing ceramic extruded brick wall of 29 centimeters with a cement render on the outside and gypsum plaster on the inside. The internal floors are terrazzo over concrete beam and block. And we couldn't insulate on the outside at all. That was not permitted by the local legislation. So what was the initial proposals for the thermal envelope and airtight layer? Because there was a commercial premises on the ground floor, this is actually a bank, the stairwell was left out of the thermal envelope and airtight layer, and the thermal envelope and airtight layer was therefore done on a per floor basis. So you can see on this floor plan, basically the thermal envelope line. Obviously, it's preferable to do the whole building if you can. In our case, we couldn't because the commercial premises was not a part of the building itself. What did we do? We applied an internal insulation system which needed to get from 1.45 of U down to 0.19. So we did that using 80 mil of PRI insulation boards, which was dab and dot bonded to the existing wall. 48 mil of mineral wool insulation between timber studs and gypsum plasterboard. This was not what we as consultants wanted to do originally, but the worry of the developer was to minimize the amount of floor space that was going to be lost with the internal insulation system. So we had to go towards very low thermal conductivity insulation like PRI boards, which personally is not a kind of material I would prefer to work with, but this was a solution that we ended up working with. So it took 14 centimeters to do the whole internal insulation system. On the roof, it was newly built with a timber structure using 60 mil of wood fiber insulation with a radiant barrier, which you could see here to reduce heat gains in the summer. Clay tiles, 140 mil of blown wood fiber insulation, on top of 12 centimeters of cross-laminated timber. So we had a well-insulated roof to keep the heat out in the summer and in the winter as well. So some of the thermal bridge detailing. Obviously one of the difficulties in retrofit, if you can't insulate on the outside of the building, is how to resolve intermediate floor and wall junctions. They can't be resolved perfectly thermally, of course, but what we decided to do was to cut out 1.5 meters of the floor and insert insulation on the floor and on the ceiling. And that way, like you can see, the C value is still quite high, but we managed to bring the minimal surface temperatures up to avoid problems with condensation and mold growth. So as you can see here, this purple material is the insulation, and it brings the minimum temperature up to about 16.5 degrees, quite way above the 13.2, which is the limit for mold growth. So you can see some images of that detail here. So the floors were cut out, and all of the external walls had these strips of insulation inserted. Windows, we did a detail of fixing the windows in the insulation layer, on the internal insulation layer. which is a good solution for warmer climates too, because if the window itself is on the inside of the opening, you get obviously more shading from the opening itself. Air tightness. We used the PRI boards for the airtight layer on the walls. They were taped to the existing plaster in the ceilings. They were taped between boards. And then on the floors, we taped them to an acoustic membrane, which was already in the design anyway. So that's what we use for air tightness. The PRI boards, existing plaster, and a latex membrane on the floors. The air tightness gave us a lot of headaches. It was a really good learning experience. One of the examples of how not to do it is what you can see here. This was a cable that was going out to the motors for the blinds. Of course, the subcontractor who came to install these was not in any of the original meetings, so he didn't know what air tightness was all about. He didn't know anything about what you needed to avoid, so he just drilled a hole through these things and stuck his cable in and left, and he was happy with the job done until we came to do the blower door test, and of course we saw all these holes. So they had to be taped up, and of course you can never get a really good tape seal like that. These are things that you learn obviously doing all of these projects. So one other problem we found actually with the air tightness was one of the flats was sold and the client wanted to move one of the bathrooms. So the drain pipes were then therefore moved. And we couldn't see when we did the final blower door test if that had been well sealed or not. So these are all the things that you can come to learn doing these projects. So the windows were taped from the PRI boards across the pre-frame onto the fixed frame. Blower door test gave us results of between 0.78 and 1.03. On the lowest floor, we actually had to ring up the bank that was on the ground floor and ask them if they could let us into the vault, where they keep all the gold and the money and stuff, because we had to actually see if there was a leak. We had a result of 1.2, I think it was, and there was a leak, which we had to inspect. So we didn't manage to take anything with us from the vault, but we did manage to get the final result down to 1. So that was air tightness. Another of the things that we looked at in the design phase was transient dynamic hygrothermal modeling to make sure that we didn't have a risk of moisture and mold growth with the internal insulation system. So we, using the WUFI calculation program, ran some simulations of the internal insulation system, looking at the relative humidity at the critical interfaces. This is a cement plaster, ceramic brick, gypsum plaster, insulation, and plasterboard. So running some simulations, we were able to see on the green line here the relative humidity over a 10-year period of the critical interface. So that gave us an indication that the internal insulation system would be safe. Very important in these cases, if you don't have an external render which is going to keep rain and driving rain out, you have to be much more careful with what kind of insulation you use on the inside. Go for a vapor open strategy and probably go for the component method rather than the demand method. So in terms of active systems, we had a per flat heating and cooling system which included the following. A thermal generator was an air source heat pump with about 5 kilowatts of heating and cooling power. That fed a post heater and cooler battery on the ventilation system. With insulated ventilation ducts taking warm or cool air into each room. Combined with radiant ceiling panels, we couldn't use underfloor because there was not enough floor space. We couldn't use fan coils or split units because there wasn't enough space either. So the option we decided to go for was most of the cooling and heating power is done by the battery, and then the remaining power is provided by the radiant ceiling panels. So you can see a cross-section of the panel here itself. It's just a 3 centimeters of polystyrene with a 1.5 centimeters of gypsum plasterboard with a water pipe running through the middle. So for cooling, of course, we needed dehumidification, which is taken care of by this battery, and that's all controlled by a control system. And we had enthalpy heat recovery units located in each flat. So here you can see just some floor plans of the ventilation system and the radiant ceiling panels. So all of that was controlled by a control system which includes a mini server and different temperature and humidity sensors in each room. That way we could differentiate between the temperature that was going to the radiant ceiling panels and to the heating and cooling battery, which would allow us to dehumidify as we needed to in the summer and modify the ventilation flow rate. So all of that controlled via a tablet put on the wall or a mobile phone. This is all very nice, it's all very sexy, it looks very cool, and it works very well. But of course, there was 2 people who bought one of the flats who were retired people. So of course, when they saw all of these phone things and applications, they were like, we don't understand any of this. And they got quite upset. So that's obviously one of the important lessons that we've learned from the project is keep it simple. You can use all of this, and it's these systems are very useful to monitor and do preventative maintenance on a system, but the interface can be different. You can interface just with a conventional thermostat and still use these systems so that it's as simple as possible for people. That's important because I think when people move into a passive house, if there are problems, they sometimes are more likely to point the finger at passive house, you know. So the simpler it is, the better. And I think that's true in any kind of building, but especially in passive house. So here are some images of the finished flats, obviously with no furniture, but you know, they've created some nice, light, open spaces. Comments from a lot of the occupants is the silence is amazing because they're right in the city centre of Girona, so there's lots of noise from bars and restaurants. Silence is amazing. It's very comfortable. You know, people are generally happy. There's been some difficulties in terms of people getting used to not having a big cooker hood. There's one couple that forgot to turn on their cooker hood, so they started complaining about smells. All the normal things you'll find in any kind of project. But I think one of the things we've learned is the handover needs to be good. You know, there needs to be good information going to the users so that they know how to use the building and run the building. So, just to summarize some of the conclusions and the lessons that learned. I mean, you know, this I think applies everywhere. Be clever and keep it simple. You know, all of us who work in passive house, we love going into detail. We love lots of numbers and graphs and details. But I mean, the simpler it is, the better. And I think Germán summarized that really well in his presentation, and Lloyd was commenting along similar lines this morning. So that's definitely a key lesson. In terms of air tightness, I think what we learned on the job is it's very important to convince the contractor to name one person on site who is the air tightness champion. That person should be the one who's going around always checking on the air tightness, because if you're a consultant, or even if you're an engineer, you're an architect, you're not going to be on site all the time. That's the first thing. The second thing is you might have lots of meetings with people, but there's always going to be some subcontractor who wasn't at the meeting, and they don't know what air tightness is or what the airtight layer is. So it's useful to have somebody on the contracting team who's on site all the time, just responsible for that. Also with retrofit projects and new build, but when you do a multi-story residential, it's obviously really important to do preliminary blow door testing on each floor. We didn't do that on 2 of the flats, and they gave us a lot of problems. So that's an important lesson that we've learned. Regarding retrofit projects and moisture damage, I think one of the things we learned was what I mentioned about the woofy simulations is, if you have to insulate on the inside, consider whether there can be lots of rain coming in and coming through the material. So if you don't have a render, for example, if you have a stone wall, a faced brick, and you have driving rain which can bring moisture in, think about going with the component method and use a vapor open strategy so that the wall can dry to the inside and the outside. Going for the demand method can be a bit more risky if not. I think it's also preferable to separate heating and cooling from the ventilation system. As you could see, put the heater and cooler battery on the ventilation system, which is a classic passive house solution. But It can create problems with noise. It can create low relative humidity in the winter if the air change rate is too high, and it means you don't have local control over each zone. So I think that's probably preferable to separate them. Dehumidification is best to do internally only. We had the cooling battery on the outdoor air supply, so of course you're dehumidifying outdoor air which has more moisture in it. It makes obviously much more sense to dehumidify by recirculating indoor air and so on. So that's an important conclusion. Basically, I think what we've learned from the project is that EnerPHit can be done in one big jump. I think it's technically and economically viable for existing buildings in Spain. I'm sure that's the case here in Portugal too. And of course, we need to work further to optimize all of these solutions, reduce costs, help training, influence the administration to provide financial incentives, and so on for the uptake to be increased. And more than anything else, the great thing about EnerPHit and passive houses is that it's a team sport. You know, everybody's involved, down to the guy who's just taping tapes on site. So that's I think, one of the most positive things about all of this. So thank you very much. Obrigado.
Thank you.